As the global population continues to soar, so too does food demand. This increase in demand, alongside a dwindling arable land area worldwide, means that novel and modern techniques for growing crops are sought after now more than ever. It is the hope of this project to design a prototype modular farm that can be implemented anywhere in the world, achievable through investigations of current technology, hardware implementations in the form of a scale model, and simulations into scalability under different conditions.
Her model was made to be trapezoidal in shape so that the expected crop yield in different spaces could be analysed. 510 lumen per metre red and blue LED strip lights were used to provide artificial lighting. Humidity and temperature sensors were placed in the structure. Plastic growing trays of different sizes were placed on each level of the farm. The whole structure was wrapped in tarpaulin to keep the light intensity and temperature in the farm. Over the farm's 3 levels, a total of 155 plants of kale could be placed to grow.
For obtaining the power measurements and sensor data of the vertical farm over the 30-day consumption period, software was used in the project. Over the internet, the ESP32 first collected all sensor data, compiled a packet of information which was then sent over through HTTP to Google Cloud for data logging. The following picture shows the experimental setup for testing both the software and the sensor components. The ESP32 first obtained the UTC time. It then checked whether the pump should be on for 30 seconds or off for 2 minutes. It then read all sensor data, compiled a packet of information which was then sent over the internet, the corresponding Google spreadsheet. However, due to limited resources and time, a scalable practical model is very limited, therefore a simulation model is required.
The model starts by calculating the size of farm needed based on population, demand and growth potential of the product. The model then finds the power consumed by the LEDs and water pump. Adding these together, we found the total power consumption of the farm. The group then aimed to find how realistic it would be to power the farm only using renewable energy produced on site. The group used power generation data based on a 150 kilowatt wind turbine in Orkney. The output of the model showed a comparison of power generation, which is the blue line, and power consumption of the vertical farm, which is the yellow line. This 2-week sample highlighted the problem with using only wind power. When wind speeds were too low, there was not enough power generated to meet the demand. The conclusion was that it would be possible to run the farm using a combination of wind power, solar power and battery storage, but it would be very expensive. However, it could pay off in the long term.
Results yielded from the case studies, hardware model and simulations provide insights into the key principles that underpin a working vertical farm. Therefore, the group can put forward its own design concept for a modular farm that can yield a high density crop output year-round, whilst generating its own renewable energy on site, removing the need for a grid connection. With the potential for scalability and functionality worldwide, it is hoped that this design can take on the challenges that will surely face the world in the coming years.